In this video, we would like to solve this exercise. So we are going to use triple integration to compute the volume enclosed between the sphere of radius 4 and the plane z equals 2 in the first octant in R3. I think the first thing that we should do is sketch a picture of this volume. So we want to compute the volume of a shape. Let's give a good picture of that shape. I will actually show you two diagrams over the course of this video. I'm going to start with one where we're kind of looking at a three-dimensional picture. Take a moment on your own to sketch a picture that you think will work for you. Here are some tips. Please make your picture large enough that you can do things like add line segments, labels, that sort of thing. Sometimes when I ask students to draw a picture, it's almost like they want to see if they can fit it between two lines on their notebook paper. Please make it a large picture that you can really work with. Here's the first of two diagrams that we will work with. So this one is very three-dimensional. We really see the volume here that we are trying to compute. It's enclosed between the plane z equals 2 and the sphere of radius 4, which is like our spherical cap on this problem. I said that we were going to do this with a triple integral. So my next question for you is how? So what is the correct approach through triple integration that will compute this volume here? And given that we're going to do it three different ways, I want to come up with maybe the general principle, and then I'll also write down how it will look for the three computations that we do. The general principle is that if we want to compute this volume in three-dimensional space, if we can take that volume, which we've named E, and describe it with coordinates, then what we can do is say, okay, let's triple integrate over that 1 dv. Okay, this is the general principle. To compute a volume in three-dimensional space, it's going to be a triple integral. The integrand is 1. We have to figure out what the right bounds are for the coordinate system that we're working with, and then put the correct volume form. So let me just write out. The bounds are what we're going to spend a lot of time on. So we will talk about how to come up with correct bounds for this exercise. So I'm just going to leave it as triple integrate over this region. 1 dz dy dx. These could be ordered differently, but I think that we will set it up dz dy dx. So that will be for rectangular coordinates. Then for cylindrical coordinates, we will say, okay, given some radial notion in the xy plane as well as some angle that we make with the positive x-axis in the xy plane, together with z, so cylindrical coordinates, we'll figure out those bounds to set up the bounds for our triple integral. And then what was 1 dz dy dx will turn into 1r dz dr d theta. So this will be our second solution. And then our third solution will be in spherical coordinates, where we will need to think about a spherical radius rho, the angle theta that we actually have here in the xy plane, or sorry, here in the xy plane, and then also the angle phi that rotates down from the z-axis. So we'll come up with bounds for those three coordinates. And then our integrand will be 1 rho squared sine phi. I believe when we do the differentials, it will be d rho, d phi, d theta. The integrands here are incredibly predictable because we're computing a volume. So we're going to have an integrand of 1 is a general principle. It looks like 1 dz dy dx, 1 r dz dr d theta, 1 rho squared sine phi d rho d phi d theta. What is most challenging in this problem is setting up these bounds. So that's where we will spend the most amount of time. What I'm going to do now is this version. So we want to come up with the correct inequalities to describe this volume in terms of x, y, and z. We will set up this integral. I might take it a little bit further than that, but we will not actually explicitly compute it all the way to a final answer. We will here. So when we pass into cylindrical coordinates for our second solution, maybe I should label this as rectangular coordinates, this is cylindrical coordinates, this is spherical coordinates. We will actually just go ahead and do the volume in cylindrical coordinates, and then we will set up but not evaluate the volume in spherical coordinates. Were you to do all three integrals, of course, you should get the same answer. For the first triple integral we write down, which will be with rectangular coordinates x, y, and z, we need to come up with a set of three inequalities which describe this region here. Looking at this, I would like to visualize this region as between two graphs of the form z equals f of x and y. The lower one has been explicitly given to us as z equals 2, and then the sphere I could solve for z as functions of x and y. What that tells me is that I'm going to have z as my innermost bounds on my integral, because again, I might need both x and y to describe inequalities for z. That's often the case in multivariable calculus, so what I'm going to do now is focus on x and y. If I imagine placing the sun along the positive z-axis and shining a shadow for this region down onto the xy plane, I would like to come up now with a pair of inequalities for x and y, which describes the shadow that we form. So that's like a quarter disk here in the xy plane. Okay, we need to say that, x is between two bounds, y is between two bounds. Let's see, if I want to place x on the outside, then I will say that x is between this number and this number. So your outermost bounds must always be constant. So I want to pick one variable and say, here's its lowest value and here's its highest value. For x, that's going to go from 0 to whatever this number is. So this needs to be determined. And then once I know that x is between 0 and this number, I'm going to say, well, how do I get the corresponding y coordinates for any point that's in this shadow? Well, y starts on the x-axis and goes out to the arc that is our quarter circle. So I'm going to say 0 and to be determined. Take a moment to see if you can work out this number here. To do that, look at how the sphere intersects the plane z equals 2. So we need to better understand this intersection here. Whenever you're looking at the intersection of two objects in math, you want to tie the information that they give you together. So for, say, this particular point, it is the case that both it lives on the sphere of radius 4 and it lives on the plane z equals 2. So let's bring that together. Let's see, I'm going to do it here. On the one hand, the xyz coordinates would satisfy that x squared plus y squared plus z squared equals 4 squared, but also z equals 2. It's like if both of these statements are true about any point which lives on this intersection. Okay, but if z is 2, then I can substitute it in for the z expression in our spherical equation, and that tells me that x squared plus y squared equals 12. So what is the value of this point out here on the x-axis? It occurs when y is 0, so x is the square root of 12. You could write that, of course, as 2 square root of 3. I think I'll just leave it as square root of 12, like that. And likewise out here, this is also square root of 12, just to kind of fully diagram out this shadow. So looking along the x-axis, for the shadow region down here that we have in the xy plane, the lowest value for x is 0, and the highest value is the square root of 12. Those are going to give me the outermost bounds for our triple integral and rectangular coordinates. A common mistake that I see students make at this point is they say, that's also true about y. Y also goes from 0 to the square root of 12. But that is not the right description for this quarter disk. Because if we try to describe this quarter disk by saying x goes from 0 to square root of 12, y goes from 0 to square root of 12, what we actually describe is a square. It would include points like out here inside this square that are not in the quarter disk. So once I have picked x to be the variable bounded between two constants, I now need to say, how for any such choice of x between 0 and the square root of 12, what values y takes. Okay, let me say that again in just a second. First, I'll draw a picture. Okay, this was supposed to be a quarter disk. If I choose, say, this x coordinate here, what are the values of y that have this x coordinate but which stay inside of the quarter disk from here to here? If I pick this x coordinate here, the corresponding y values, which would produce xy coordinates inside of the shadow, inside of this quarter disk, go from here to here. So what we realize is that the upper bound for y is not the constant square root of 12, because that's going to include points in this square, looks like a rectangle, it should be a square, which are outside of the disk. Instead, the upper bound needs to be coming from this quarter circle equation. That quarter circle equation is here. This would be the circle of radius 12. I need to solve for y. So y squared equals 12 minus x squared. So since we are working in the first quadrant where y is strictly positive, we take the square root of both sides, and we get that the appropriate upper bound for y is going to be the square root of 12 minus x squared. This pair of inequalities together describes this quarter disk in the xy plane. I don't want to keep saying this too many times, but again, if you just said square root of 12 here, you would be describing a square, not a disk. Once I've identified that x is going to be bounded between two constants, somebody has to be between two constants, so it's going to be x here. The description for y then needs to go from here to here, not from here to there. So y is bounded between 0 and a function of x. Okay, let me step aside and I'm going to erase all of this, and we will now provide well, I'll keep this actually, but I'll erase this, and we will then look at the right inequalities for z. To finish our description for the region E with inequalities, we need to also give inequalities for z. And how I would like for you to think of this is, imagine that we take a journey straight upwards parallel to the z-axis. Where do we enter the solid and where do we exit the solid? So as I travel upwards, I always enter on the plane z equals 2. So the lower bound of 2 is pretty immediate. Everywhere we travel up through this region here, we start in the plane z equals 2. We exit when we get to the sphere. So for example, my journey could look like enter here, exit there. More towards this corner, it's like enter here, exit there. So the upper bound for z needs to come from how z varies as a function of x and y, because where we exit depends on where I am in this disk. So the mistake I see students make in this kind of problem is they will say the upper bound for z is 4 because that's the highest value that z takes. But that is not the correct recognition here. It's the same misconception that might lead someone to write that y goes from 0 to square root of 12 in this set of inequalities. Instead, we realized y is being cut off by a function of x. Here, z is being cut off by a function of x and y. And it comes right from the equation from the sphere. So if x squared plus y squared plus z squared equals 16, that's the equation of the sphere. That's what's defining the shape up here. Solving for z and recognizing that z is strictly positive here, we can say that z is the square root of 16 minus x squared minus y squared. Okay, so this will be the outer set of bounds because x here is bounded between two constants. This will be the middle. Y needs to come in the integration before x because one of our bounds depends on x. And this will be the innermost set of bounds because z here is bounded by a function of both x and y. So as I predicted, our differentials will be dz, dy, dx. Take a moment to set that up. Before I step away, let me just mention that if you had said x goes from 0 to square root of 12, y goes from 0 to square root of 12, z goes from 2 to 4, you would not be describing the shape at all. You would actually be describing a rectangular cube. So if that was your inclination, it might help you to compare a rectangular cube, recognize why constant bounds are correct for that, and then realize if it's not a rectangular cube, you need to bring in the correct equations which give you the real shape of this region. The inequalities that we just wrote down to describe this three-dimensional solid now become the bounds of this triple integral, where again, the outermost bounds are the constant ones, so that's dx on the outside, and then since y is being bounded between 0 and a function of x, that needs to come before x, and then z is bounded between 2 and a function of x and y, so that has to go on the inside. Other orderings are possible, but this is, I think, the most standard way to set up this triple integral in terms of x, y, and z. We are done with what I wanted to do for a triple integral in terms of x, y, and z, but let me take this just a little bit further. Were I to start integrating this by hand, I wouldn't really want to because of all of the square roots, but let me do one round of the iterated integral. So I'm going to anti-differentiate with respect to z. Well, if I do that, I'm going to turn this one into a z, and then plug in top and bottom bounds. Here's what I would have after one round of integration. Okay, I don't know why I struggled to write that. Let me keep going. 0 to the square root of 12 minus x squared. And then again, the antiderivative of 1 with respect to z is z. Plug in the top, and then subtract off 2, and we're left with integrating this with respect to y and then x. I'm certainly not going to integrate this particular expression any further, but what I wanted to point out is that it is possible to look at this solid and say there's a double integral that would do the same volume computation. And this is that double integral. The principle here is top minus bottom. So it's like if I started here, I would think of this shadow down in the xy plane as my domain of integration. And then I would say what we're integrating is the difference between two functions of x and y. It's analogous in single variable calculus to when you compute this area between two curves by saying it's, f minus g as your integrand. I really didn't want to mix this in too much. I just wanted to point this out in case you looked at this and wanted to go straight to a double integral. This probably was that double integral, and it is related to the original triple integral. So while I think of this as a volume computation, it is connected to a slightly different approach. And I want to leave it there because ultimately in this video, I want to focus on this idea. So let's now revisit this solid, but this time we are going to describe it with cylindrical coordinates. It's actually very fast because we've done most of the work. So let me step aside and I would like for you to take the cylindrical description as far as you can. What you want to find are bounds for the radial coordinate r and the angular coordinate theta for this quarter disk down in the xy plane. Z will still be z, but what we described earlier as z trapped between 2 and a function of x and y, this needs to change because we are switching from x and y to r and theta. The quarter disk is actually nicer to describe with r and theta than x and y. And again, we've already done most of the work because we realized that this outer radius was square root of 12. So looking at this solid quarter disk in the first quadrant of the xy plane, you can recognize that theta is probably the most immediate. That goes from 0 to pi over 2. And then r is also going to be nicely bounded between constants because if I follow any ray outward from the origin, so I imagine starting at the origin in the xy plane and I radiate outwards until I'm at the edge of my shadow, then the bounds on the radial coordinate are always going to go from 0 out to the square root of 12. So this is, in my opinion, nicer because when we set up the integral, which we can actually start to do, we have a pair of bounds which are both constant. Okay, for z, we are still going to call it z. It's still the same coordinate that travels in this direction. We just need to make sure that any bounds we place on z are, if anything, expressed in terms of r and theta. The lower bound for z is still 2, because if I imagine following the z direction straight up, I enter the solid on the plane z equals 2, and then I'm still exiting on the sphere. So our geometric understanding of how the z-coordinate varies through this region is still correct. But now I want to take the description I had in terms of x and y, which was 16 minus x squared minus y squared, and I need to replace this. This is the kind of thing you want to learn to spot really quickly. For one thing, I can rewrite this as 16 minus x squared plus y squared, meaning I can factor the -1 in front. Okay, like that. So basically pull this -1 in front of the x and y terms, and you get 16 minus x squared plus y squared. Again, recognize x squared plus y squared. In polar coordinates, x is r cosine theta, y is r sine theta. So any xy coordinate in this quarter disk could be computed in terms of the radial and angular coordinates this way. And this is just something that you must know when you're passing between rectangular coordinates and polar coordinates, is that with this standard definition, x squared plus y squared is r squared. That comes from the Pythagorean identity. So this is something that you must recognize when you're working with this coordinate system. Therefore, when I see 16 minus the quantity x squared plus y squared, my mind goes straight to r squared. And I think it looks nicer. So nice, in fact, that we are going to integrate this by hand. The integrand goes to 1r, because we are changing coordinates into cylindrical coordinates, 1r dz dr d theta. In a moment, I'm going to just go ahead and integrate this so that we actually get a number that tells us the volume of this region. Let me just say a quick vocab remark, because I switch back and forth between cylindrical coordinates and polar coordinates. To me, when I'm just thinking about this pairing, I call that polar coordinates. So when I was thinking down here, I may have said polar coordinates. And then when you incorporate z as well, so that you can imagine taking a radial and angular coordinate and pairing it with some kind of z altitude, for me, that's cylindrical coordinate. So if you're wondering why I mix the two expressions together, that's why. Okay, again, I'm going to erase this, and we will actually go ahead and compute this volume before we wrap this up with spherical coordinates. Let's just jump right into it. There's not too much tricky here, so I will do immediate anti-differentiation with respect to z. This will become rz, and we need to plug in the top and bottom bounds for z. We will have a subtraction here because we'll plug in the square root of 16 minus r squared, and also 2. I'm going to break it into 2 integrals as I do that. So my first one will go from 0 to pi over 2 for theta, and from 0 to the square root of 12 for r, and then I'll write r times the square root of 16 minus r squared dr d theta, and then subtract from that the other one, which is actually just going to be 2r, the integrand. So that's nice. Like so. This is going to be a u-substitution. So we look inside the square root and we see this r squared, and we recognize that the derivative of that is 2r, and we see an r out here. So that's where your mind should go when you see that expression. So let's have u be 16 minus r squared, so that -1/2 du is r dr. I did a lot there at the same time, so I'm going to just see du would be negative 2r dr divided by negative 2, and we get negative 1/2 du is r dr. Okay, we'll change bounds as I rewrite this. And I think the other thing I will do, I'm just trying to see, is I'll leave the first one alone. I'll do it for the second one. Okay, let's do 0 to pi over 2. We need to change our bounds. When the original variable r was 0, u is 16. On the other hand, when the original variable r was the square root of 12, u is 4. And then we have a negative 1/2 square root. So r dr here became negative 1/2. I'll write du in a moment, but then square root of u, let me write that as u to the 1/2 du d theta. And then I'm going to do something to the second integral, which I will also do to the first one in just a moment. I just wanted to do it once first. And that is recognize that this double integral has constant bounds, and the integrand can be separated into a function of theta times a function of r. And let me actually do that separation with no anti-differentiation. So I'll just do it one step at a time. What I'm going to do is take this and pull out the 2 and write this as 0 to pi over 2, 1 d theta times 0 to the square root of 12. Oh, actually, I'll just write r dr. Okay, that's optional, but when you recognize that a double integral has constant bounds and the integrand can be factored into a function of r times a function of theta, you can actually take the double integral and split it into the product of two single integrals. Again, it's optional. I just like to do it. Okay, I'm almost out of room, but I think I can do one more line here. And I'm going to do that here as well. I'll do a lot here. I'm going to pull the negative 1/2 out front, 0 to pi over 2 d theta, 1 d theta. And let me flip my bounds, throw a plus sign there, 4 to 16, u to the 1/2 du. Okay, so I did the same thing here where I had a double integral with constant bounds, and I recognized that the integrand could be factored. So I separated it into the product of two single integrals. I pulled the constant 1/2 out. I also flipped the sign by flipping the bounds here. This looks fine to me. Here I'm going to go ahead and integrate. So this is going to be theta going from 0 to pi over 2. And this is going to be 1/2 r squared, 0 to the square root of 12. Okay, apologies if you couldn't hear me just there. At this point, it's very routine. So in a moment, I will come back and I will have moved this up so that we can just finish quite quickly, because at this point, there's nothing too exciting left about any of the computation here, but we can go ahead and get all the way to the end so that we can say what this volume really is. This line is exactly where we left off. Integrating this, it's going to be pi over 2 minus 0. That's what we have here, actually. It's the same single integral that we had split off earlier. So let me go ahead and write 1/2 times pi over 2 minus 0. And then here, this will be u to the 3/2 times 2/3. And u will go from 4 to 16. And then minus, if you saw me hesitate earlier when I pulled that 2 out, it was because I recognized that this was going to happen. We have pi over 2 minus 0. I will just write pi over 2 times, here, 12 squared minus 0 squared. Okay. Let's keep going. We have another cancellation here and here. So that overall, this is pi over 6. I need to do 16 to the 3/2 minus 4 to the 3/2. I think the easiest way to do that is to recognize 16 to the 3/2 is 16 to the 1/2 cubed. So it's square root of 16 cubed. Just make it clear what I'm doing here. Square root of 16 cubed minus the square root of 4 cubed. And that's nice because those square roots are perfectly pleasant. And then here we have minus pi over minus 6 pi. Okay. Pi over 6. And then square root of 16 is 4. Cubed is 64. Minus 2 cubed is 8. And then if you actually work out what this number is, it should be 10 pi over 3. Which is, of course, perfectly possible to get, but at this point, we're just crunching numbers. Okay, so the volume of this region here is 10 pi over 3. Although we spent a lot of time on this computation, the secret take-home message of this exercise is that cylindrical coordinates is the best. So there's a reason why I picked cylindrical coordinates to proceed. We are now done with cylindrical coordinates, though. So for our third and final look at this region, we will describe it with spherical coordinates. For that, I'm going to give you a different diagram, one which I think is a little better when we're looking to figure out particularly the spherical radius rho and the angle phi that we rotate down from the positive z-axis. What I would like for you to do is imagine that you took the x-axis over here and kind of pointed it right at your eye, and maybe the xy plane was flat for you, so that you would see this almost like a flat picture. If that made no sense to you, that's okay. I'll come back and put up a diagram of what I'm trying to explain. Here's the diagram that I propose using for spherical coordinates. It looks flat, but what I want you to imagine is that this point down here, it's actually the entire x-axis. You're just looking right along it so that it looks like a point. And so this flat y-axis is really like the whole xy plane is right here. So it's kind of like if this is a tabletop, your eye is right above the tabletop and you're looking along the x-axis. The reason why I like this perspective the best is that it gives us a nice viewpoint for the spherical radius rho. So that's the radius that we get in any direction out from the origin, as well as the angle phi that we get as we rotate down from the positive z-axis. There's a third coordinate for spherical coordinates, but let's go ahead and knock that out. The angle theta is still rotation right here in the xy plane. It's the same theta as before. So immediately we know that theta goes from 0 to pi over 2 because we are in the first octant. For the other two coordinates, phi and rho, I recommend drawing rays that start at the origin and radiate outwards, cutting through the solid. We want to describe rho in terms of the distance points in this region take from the origin. Phi is like the angles that these rays make with the positive z-axis as we rotate down through the region. Okay, let's tackle these one at a time. I think the easier of the two is phi. So as I rotate through this region, as I start at phi equals 0 along the positive z-axis and then let phi increase, we will rotate through angles all the way until we reach the intersection between the plane and the sphere of radius 4. So this angle right here should be our upper bound for phi. So phi takes us from 0 out to whatever this angle is when we look at the angle formed by this ray and the positive z-axis. Okay, so that's what we're going to find right now. So I'm going to fill in this upper bound. To determine this angle, we observe that it's being cut off when, or rather our rotation in phi is cut off when the sphere and the plane meet. So once again, it comes down to an intersection, the intersection of the sphere and the plane z equals 2. What we need to do is take those two equations and first write them with spherical coordinates. A sphere in spherical coordinates is very fast to describe because the coordinate system was designed for spheres. In spherical coordinates, the sphere of radius 4 is rho equals 4. This is analogous to the expression x squared plus y squared plus z squared equals 16 in rectangular coordinates. In spherical coordinates, it's just this. The plane, let me write out here that we're looking at the plane we originally thought of as z equals 2. In spherical coordinates, this equation will just need z converted. So z in spherical coordinates is rho cosine phi. So this plane right here, z equals 2, and spherical coordinates can be represented as rho cosine phi equals 2. They intersect when both of these equations are simultaneously true. Once again, we see we have a substitution. Rho is 4, rho appears here. Let's substitute 4 into the second line. So we can say, therefore, 4 cosine phi equals 2 when the sphere and the plane intersect. That tells us cosine phi is 1/2. And notice what angle gives you a cosine of 1/2 pi over 3. Okay. So we start at phi equals 0. That places us on the positive z-axis. We rotate out, and we remain in this region right until we get to here. This is where phi equals pi over 3. If you're curious, if we kept rotating when phi equals pi over 2, that's when we hit the xy plane. So this moment occurs when our angle of rotation down from the positive z-axis is pi over 3. Let me pause here, and I would like for you to look at these rays I drew. Maybe you drew your own on your own diagram. And say as much as you can about rho. Really think about how rho is behaving as we draw different rays through this region. Returning to the idea of a common misconception that students make when they look at equalities to describe regions, I would expect a few students at least to look at this and think that the radius goes from 2 to 4, because that's what we really see when we look along the z-axis. But that's not how the radius behaves as we look at different rays cutting through this region. So I would really recommend looking at one of these interior rays that's just kind of right in the middle. You want to measure the distance that points in this region make with the origin, say for this ray. Okay, so we enter the region here. This is the lower bound for this particular radius, and then we exit the region here. And then we have every radial measurement between those two. Same story, say along this ray. I'm not in the region, not in the region, not in the region, and then I enter the region right here. I stay in the region, and then I exit the region. One conclusion that we can get pretty fast looking at this diagram is that no matter what ray you follow, you exit on the sphere of radius 4, where the spherical radius is 4. So it is true that the upper bound for rho is 4. But look at the lower bound. Here it is 2. That's what I think students might jump to too quickly. But out here, it's actually 4. Right at this intersection point, we enter and exit the region in the same moment. So here it's like the lower and upper bound for this particular ray is 4. So we vary from 2 to 4. And how I would think of this is we vary as the angle phi rotates us through this region. So if you look at this, we really have this lower bound here increasing from 2 to 4. And what's the deciding factor? It's the angle of rotation in phi down from the positive z-axis. So that means that this lower bound here should be described as a function of phi. If you didn't see that a moment ago, pause to think through that and then see if you have an attack strategy. So how do we come up with a relationship between rho and phi that will allow us to characterize that lower bound for rho? If you look at this diagram, maybe particularly as you circled it, as you did that, it would jump out to you that the relationship between rho and phi is really going to come from the plane z equals 2. So remember, what we just wrote down. The plane z equals 2 in spherical coordinates is rho cosine phi equals 2. And now this is an equation telling us how rho and phi relate to each other on this plane. So in particular, if I want to think of rho as a function of phi, I can say rho is 2 over cosine of phi, or in other words, it's 2 secant phi. Let's just check this. When phi is 0, I'll use this equation because cosine values are more known to me. So when phi is 0, cosine of 0 is 1, rho is 2. And that is indeed the rho value here. When phi is pi over 3, cosine is a half. 2 divided by half is 4. And we said that this was length 4. So you can see that as phi changes from pi over 2 to pi over 3, rho is going to change from 2 to 4. So this entry point into the region grows from 2 to 4 as phi varies. So the bounds for rho are from 2 secant phi to 4. We just need to put this together into a triple integral in spherical coordinates, and then we'll be done. We have 3 inequalities here. 2 are constant. Either could go on the outside. I like to put theta on the outside, so I will do from 0 to pi over 2 for theta, and then from 0 to pi over 3 for phi. And then since rho depends for its lower bound on a function of phi, that must be inside relative to the rho bounds, so it makes sense to have it as the innermost integral here. It will go from 2 secant phi out to that constant value of 4. It's going to be 1 rho squared sine phi d rho d phi d theta. D rho d phi d theta. Okay, I hope you enjoyed this exercise thinking over how to describe this region using 3 different coordinate systems. If you're wondering what my preference was, I think I said this earlier, but it would be cylindrical coordinates for this problem. Okay, thank you for your attention.